I wanted to start by thanking the organizers for putting together a wonderful workshop and in a beautiful location. I hope that if you haven't yet done so, that you enjoy the woods and take a walk. We certainly found yesterday some beautiful sculptures unexpectedly in the woods, so I encourage you to explore and enjoy. Of course, the biggest enjoyment is the science, and today I'll be telling you some of the work that my group and our collaborators have been engaged in connecting individual spins to photons and looking more broadly at the quantum transduction problem. How do you get information between two different locations for quantum information applications? This work is done primarily at the Joint Quantum Institute and the Joint Center for Quantum Information and Computer Science, which are based at the University of Maryland, and are joint at the National Institute of Standards and Technology, which is where I work. This is a science talk. If you have non-science questions, I'm happy to take them on a one-on-one. So why quantum transduction? When we talk about quantum information science, we talk about the promises quantum mechanics makes. These are the assurances that we have, insofar as quantum mechanics is our fundamental theory, that the universe makes. And these assurances include limits on measurement science in the form of the Heisenberg uncertainty principle and its applications and implications. These include the role entanglement plays in everything from determining the structure of space-time to making shared randomness a resource for key distribution and cryptography, to building new states of matter, where we can characterize these new states by their amounts of entanglement. All of these things are really intriguing. The one I'm going to zoom in on today is what we might call quantum networking, which is building and using entanglement between systems at some distance. So I'm not so interested in the entanglement intrinsic in the hydrogen molecule. I'm also even not so interested in the entanglement intrinsic in the fractional quantum Hall state. I'm more interested in the sort of diaphanous entanglement that we create in the laboratory setting, where we try and get two isolated systems, get them just coupled in the right way to entangle them, where the distance scale becomes large. And this is what we might call quantum networking. What does quantum networking enable? Well, we've seen already in the last few years some beautiful new physics tests, Bell's inequalities tests so far, which have finally closed all of the loopholes in the Bell's inequality story. And I think that there are more opportunities for exploring fundamental physics using entanglement at distance, where we can start to ask questions about spontaneous collapse theories, about theories of gravity. And if you haven't been keeping your ear to the ground and listening, you may not have realized that these concepts are really starting to take over in the high energy theory community, in the dark matter communities, where they're trying to come up with new mechanisms for testing. And so as people working more on the laboratory side, let's say, than the pure theory side, I think it behooves us to pay attention to those opportunities. There's also some new approaches for metrology. I'm not going to talk about that because I believe that the talk after mine is going into some of this. There are some things like shared randomness at distance, which is known primarily as quantum key distribution, but for example, at NIST, we're using this to create what's called a random number beacon, a device that produces certified random numbers, certification being given by quantum mechanics. There's also interesting prospects in distributed quantum computing, which I will talk about at the end of the talk. And then finally, very long term, there's a whole category of interesting algorithms, which are network algorithms. And probably the most prominent of which is blind computing, in which a cloud server, in this case the quantum cloud server, executes a program on your behalf, and it knows neither the program nor the data that it executed. This is possible, provably possible with quantum mechanics, and it's something that we have not found a solution for classically. So quantum networks provide these opportunities, but of course we still need a way to get the quantum information from A to B. Putting on my metrology hat, there's a little bit more to the story, because it turns out quantum transduction is the thing that connects up two quantum memories. It is also a device that we can take incoming very weak signals, signals at the quantum limit, and put them into another media, another means of detection, which might be much easier for us to measure. And so quantum transduction, work done here to build quantum networking, also has applications here in measurement science. And I will occasionally highlight those applications, perhaps at the detriment of the quantum story up here. Okay, so those are kind of my opening remarks. I'm now going to spend a little bit of time talking about single spins. And I thought perhaps there would be prior talks in the workshop focused on single spins, but I was disabused of this notion when I read through the whole abstract list. So I have to tell you a little bit about single spins isolated in quantum dots, an area that you may or may not know that much about. And so I will go relatively rapidly, but I encourage you to ask me questions so we get this right. Because if you don't understand this, the rest of the talk will be incomprehensible. So what is a spin in a quantum dot? Well, a quantum dot is a local confinement of electrons in a semiconductor. Usually we provide this by a combination of band structure engineering, so that electrons are confined in some reduced dimensional space, like a two-dimensional electron gas or one-dimensional nanowire, and then electrical gates, which provide additional electrostatic confinement. If these gates on the surface of this computer chip, of this here, a 2-DEG chip, are charged up negatively, they repel electrons buried in the chip below, and that can create a potential island that traps the electrons. The charging physics of those small islands, they're very, very small capacitances, lead to quantized amounts of charge on each of the islands. And these quantized charges, when they're an odd number, have a overall spin half, or at least Cramer's doublet character. So we can call that Cramer's doublet up or down, maybe or 0 or 1 if you prefer. And I will kind of make a theorist replacement of that double well potential represented there by just 2 little potential wells with an electron in each. I happen to like this particular architecture, part because they're relatively stable. Like once I fabricate the chip, I can use it many times. The possibility of local manipulation, so really working down at the nanoscale, is enabled by these electrical gates. Right? They let us work at very small length scales. And then there's also some possibilities of large-scale integration by leveraging existing CMOS technology, though I think this has been something that is more of a gesture at an unknown engineering space than a real scientific statement. Why spin rather than, for example, charge degrees of freedom or superconducting degrees of freedom? Well, of course, the main thing is that in these materials we have a lot of phonons. And the phonons couple to the charge pretty easily. Now, that's something that in superconductors we get around through the BCS pairing mechanism, but in semiconductors we're stuck with it. So you want to stay away from the charge directly. It also gets rid of some of the coupling to various sources of noise in the system, mostly phenomenological noise sources associated with surface traps and other unknown, honestly, noise sources, which we often characterize as so-called 1/f noise. But there is a basic trouble. All these things are good, but the problem is that the magnetic dipole is weak, right? It is a higher order in QED, and we have to come up with some ways around that. So in many of the talks prior to this one, you heard about mechanisms for getting around that that relied upon magnetism, a very powerful phenomenon, which I will not leverage to make our success. Instead, we're going to come up with spin-orbit approaches, where we maximize the spin-orbit coupling to get that spin coupled to electric and magnetic fields. Where are we? Well, the coherence times for single electrons in quantum dots are now getting to the 100 microsecond range. Coherence times of single electrons on impurities are actually even better, where, in fact, the world record in coherence time is now held by a single phosphorus impurity at about 10 to the 4 seconds. It used to be on beryllium ions, but back in 1993, actually. But you know, a few years ago, finally, that was surpassed by about an order of magnitude. Of course, fundamentally, you have different trade-offs you make between working with these dots, where the length scales are larger and the gates are relatively fast, and the impurities, where length scales are smaller and the gates are slower. If you thought much about engineering, you understand that actually 100 nanometer scales are much easier to work with than 5 nanometer scales. So yes, it's wonderful to pack lots of qubits in, but no, it makes it really hard to do anything with it. So we have to be a bit careful about that. Okay. So let's now focus in on my particular topic zone, which is not just spins in semiconductors, but spins in silicon, trapped in quantum dots. And that will now form the basis of the next 10 minutes or so. So where are we sitting? We're sitting at low temperatures in the millikelvin regime. We want to be at low temperatures in order to freeze out orbital degrees of freedom and really work only with the spin. We also want to be at low temperatures so we can easily initialize the system in ground states using coupling to a Fermi C. We manipulate the system using microwaves, primarily. So modulation and pulses operating in the gigahertz regime. The qubits are relatively small. How do we couple them together? Well, this is actually the key question. How do you get the qubits entangled? One approach is that you literally have the electrons run into each other. So when two electrons overlap, the Pauli exclusion principle starts to play a role. If you think of like a Hartree-Fock theory, you can say, well, there's a sort of Hartree type term, which is like a Coulombic interaction of particles with no interesting statistics, and then there's the Fock term, which is the interesting statistical term, which corresponds to the fact that the electrons can't be in the same state. And this we characterize as the exchange interaction. And what is the exchange interaction? It is the two electrons basically flipping with each other. So if they have spins, they're going from up down to down up. This exchange interaction we'll use quite a bit. But there's also some other approaches. So these things do have some weak dipolar moments. So there is a direct dipolar coupling you can induce. And Miri Jacobi's group has had some success doing that. And then there's also the possibility of electrodynamic coupling. So rather than directly coupling the electrons to each other, you couple the electrons to a virtual photon or a direct photon, have it travel some distance, and then couple back to an electron. That type of bus architecture underlies ion trap computing and now superconducting computing, and it may also underlie spin computing if we can come up with that mechanism, which lets us get past this sort of 100 nanometer scale and out to the millimeter to centimeter scale. And I'll talk near the end about some of the architectural considerations that make this very compelling. But at the present time, we're in a community where we like the concept of spins and cavities talking, so I'll motivate this no more. I want to return now to the exchange interaction because we're going to have to work with exchange in order to get the coupling to make sense. So what is this exchange interaction? Well, think about two electrons trapped in two nearby potential wells. And here I'm just showing that their spin because essentially I'm saying all the higher orbital states are too high in energy to matter. So you know that if the electrons can join together in a singlet, that the virtual tunneling process of joining together in a singlet and then coming back, or you can come back in either one of the two spin states, that virtual tunneling process is allowed because the Pauli exclusion lets two electrons fill the same orbital if they're opposite in spin, if they form a singlet. So you have a virtual process that reduces the energy of that configuration, whereas if they're in the triplet configuration, you don't get anything. Forget about that for the moment. So the key difference here is that the singlet configuration of the two spins, even though they're in two separated dots, ends up producing the lower energy state, and then the triplet configuration ends up producing a higher energy state. The difference between these is the exchange energy. It also means that, as I forgot to show here, let me show here, means that when I manipulate the electron spins by, for example, a global field that drives them both, the triplet state moves around, but the single state is static. Nothing happens to it. Right? So these are obviously fundamentally a two-qubit kind of basis, an entangled kind of basis. And that being said, we've been able to make a lot of progress by understanding it better and better. So here is a typical diagram that we use to understand these types of systems, where I've got a double potential well with a sort of symmetric configuration of them here, and then I can bring this right one down further and further to make it asymmetric, as I've done here. And at some point, the well gets low enough that the Coulombic energy scale is overcome by the lower potential energy, and the electron wants to tunnel over. But it only does so if it's in a singlet configuration, because the triplet configuration requires filling a higher orbital state, which is much higher up in energy. So you get an energy level diagram that describes the system looks a bit like this. I have an avoided crossing through the tunneling mechanism for the singlet configuration. Here is singlet split left-right. Here's a singlet on the right. But the triplet configuration does not tunnel. And now you can see that manipulating a gate voltage on the bottom here, which changes this difference in height, moves the energy of the singlet compared to the triplet. So this is kind of nice because it allows you to do two things. First of all, I can control the exchange interaction with the voltage. And you'll notice that a cavity field will have the same action on this object. And the other thing is that if I started over here in the singlet triplet configuration, the charges are almost all the same. But if I adiabatically go through this avoided crossing over to here, the charge state of the singlet is very different than that of the triplet. And that allows us to read out this entangled basis by using a nearby electrometer. Also, typically a quantum dot, but sometimes a quantum point contact, or sometimes an RF single electron transistor. All of these charge readout techniques can work, but you have to, of course, have a way to measure that magnetic degree of freedom. So this is one of the more robust ways we have of actually directly measuring the magnetic degree of freedom, rather than trying to do magnetic dipole measurement, which is very hard. You know, the magnetic dipole from a single electron at 10 nanometers is only about a megahertz energy shift on a magnetometer. And if you're more than 10 nanometers away, it becomes very, very small. So single electron measurement of the magnetic part is very hard, but converting it to charge and then measuring the charge is relatively straightforward. Okay, so that's kind of setting up a little bit now that we can move around in this energy level space of two electron systems, and we can convert the electron spin. We can also actually prepare the system by sitting over here and filling from the Fermi sea. This is the ground state of this configuration. There's a large energy gap, and if I hook it up to the Fermi sea, I should expect eventually to load into that singlet configuration. So that's sort of our toolbox for getting started. And now we want to hook up this toolbox to a cavity. So let's put the cavity, so the center pin is over here, and the ground plane, center pin is over here, and the ground plane is over here. And so the cavity field is going to drop across the dot, which is going to produce a difference in the potential energies of the left and the right well. And so this was first done actually in collaboration with Jason Petta's group, and then also over at ETH Zurich, and also at RIKEN in Japan, 3 different groups. So this is the work from the Petta team where I was engaged, where they had a nanowire quantum dot, indium arsenide, which is coupled to the cavity pin and to the ground. And here is a cavity made out of a coplanar waveguide with an inductive tap, so you can flow DC current through it, so you can do DC current measurements. That you pay a high price in the cavity queue, so I don't recommend this in general, but when you're first doing the science, you need to know what you're doing. And so in that first experiment, what we're able to do is see how the different charge configurations can be read out in the cavity response. If you think about there's a cavity photon that can cause virtual transitions between the singlet and these two different spin states. In indium arsenide, in magnetic field, there's a large spin orbit coupling, and that means that I get actually different G factors in the different dots. And so rather than having singlet triplet on the left-hand side here, you have up, down, and down, up. We're going to come back to that. In other words, if the difference in energies, the ambient energy of left dot and the right dot, is much larger than the exchange energy, the preferred basis is not singlet and triplet. The preferred basis is up, down, and down, up. So this allowed us to make a measurement of individual, or pairs rather, of spins by seeing how the virtual response of the cavity changes, which you can see in the phase shift of the cavity, and you can even read out Rabi oscillations when you drive the system into coherent superposition. So it was kind of a nice example where we use this dispersive change of the cavity because of this essentially variable capacitor system that sits inside it, and in order to read out the spin states. Some people call this by the quantum capacitance because it is a state-dependent capacitance term. I don't particularly like that phrase, but you'll see it. But what is our goal? Our goal is not just dispersive coupling. Our goal is to get individual magnetic dipoles coupled up to the cavity. So now we're going to dive into our bag of tricks to try and make this a reality. I want to remind you about the challenges of getting a strong vacuum-Rabi coupling. So one thing you need to understand is that the vacuum-Rabi coupling for dipoles is actually pretty easy to work out from fundamental principles. And I happen to like this formula a lot because Tashima Mogu is the one who really put me onto this in the first place, because it just involves some fundamental constants. You have the square root of the fine structure constant when you compare vacuum-Rabi to the resonance frequency of the cavity. So that's your kind of factor of about 1/10 that you're always going to be paying because it's a perturbative theory, QED. Then there's the dipole moment compared to a Bohr dipole. That's a single electron charge and the Bohr radius. And then there's the square root of the wavelength of the resonant excitation times the Bohr radius squared, divided by the volume in which the electric field is stored, the mode volume. Magnetic dipole coupling is essentially the same formula, except you replace the electric dipole with a magnetic dipole, the Bohr dipole with the Bohr magneton, and you pay another factor of 137, right, the fine structure constant. So these are now the tools. If you want to increase the coupling, you have to play with the tools. So you can decrease the volume. You can decouple the magnetic electric field, so you have different electric volumes and magnetic volumes. This is what happens in lumped element circuits, right, where the magnetic field is largely in the inductive element, the electric field is largely in the capacitive element, so you can kind of concentrate the inductive energy, as Patrice has beautifully done, by making resonators that have a very narrow single inductive element and then a big capacitive setup. So that's one approach. And you may think of this as an impedance tuning of the resonator system. But you can also increase the dipole moment. So for example, in these original experiments from the Sholkoff group, they had this transmon, before it was called a transmon, a Cooper pair kind of qubit. They realized by replacing that thing with a much bigger antenna, they got a better transmon performance, but they also got better coupling to the cavity. So you can increase the dipole, and then finally you can just try and make the cavity smaller and smaller. So one of the great benefits of working with the planar geometries is we have a relatively small mode volume because you have a center plane conductor provided by the superconductor. So you have confinement of the electromagnetic field into transverse dimensions much smaller than the wavelength. Okay, so those are the tools. None of these are enough for the single electron coupling. Not with what we have right now. So instead of making a single electron dipole coupling, what we're going to do is use the electric dipole coupling rather than magnetic dipole coupling, and then convince the magnetic spin degrees of freedom to get an electric dipole. And that's going to be through the spin-orbit coupling. We're not going to use intrinsic spin-orbit coupling, though, because I want to do it in silicon. And silicon doesn't really have intrinsic spin-orbit. It's very weak. So we're going to have to add our own spin-orbit. So you go to the spin-orbit store, and you start poking around to see how you can make your own spin orbit. And of course, you can do it with strain in the form of Rashba. Or you can do it by adding magnetic field gradients in particular. Because a spin orbit coupling is a orbital difference in the spin, which can arise if there is a spatial dependence in the magnetic field. So what does that look like for us? So let's look at the scenario where I have the singlet and triplet. Here I'm looking just at the up, down, down, up space. So these things are up, down, and down, up. They should be degenerate with each other with no magnetic gradient and with no exchange interaction. Now there is some tunneling that takes the singlet state to the other singlet state. That's going to lower that singlet energy. Or here, we'll raise it because I took this one lower to be lower in energy. These are the three states we're considering right now. Or forget about the up, up, and down, down states because they're set off by a large amount of energy overall. I put a magnetic gradient on. And as I mentioned, that makes the preferred energy basis under the magnetic gradient to be up, down, and down, up, right? Because I have a large difference between up, down, and down, up that prevents the exchange between the two, and that prevents the singlet from being the lower energy state. Now, I still have allowed tunneling between these two states and the singlet configuration, but of course, one can be near resonant where the other is quite far off resonant. And so the tunnel coupling now starts to mix those two states. And that's a charge superposition. These are a superposition of a singlet or a spin-like partial singlet of up, down, and down, up in 2 dots, and a singlet in 1 dot. So that is a dipole allowed transition. And what we're going to work with is virtual admixture of things like that. So this is our original proposal from 2006, and then Guido Buchert had a similar, along with Atash, had a similar proposal that came out just after ours. And we kind of thought that'd be a neat way to go. But that's actually still using the single-triplet physics, and it's not really single magnetic dipoles. So let's get to the single magnetic dipole story. Don't use 2, use 1. Add a magnetic gradient. And we first did this actually with Lieven van der Sippen's group back in 2013, where we used it for exchange relaxation, or spin relaxation. But we're going to use it also for cavity coupling. So I want you to look at this double wall potential again. Now I've got electron spin left, electron spin on the right. And I've got sort of a 4-dimensional Hilbert space of is the electron spin left or right? Is it up or down? I put a magnetic field on with some difference in the magnetic field on the left side and the right side. So this is the average field, and this is the difference field here or here. And that difference field has both a part parallel to this and part perpendicular to it. When the overall Zeeman energy is large, as I've drawn here, then I can barely see the effect of this field. When it's small, so that the tunneling crosses over the different Zeeman states, so this is up, down, left, right, then I get this sort of emergence of this sort of smile feature. Some call it a frown if you look at it upside down. It's a, and these points here represent that the charge and spin are highly mixed. So in this paper in 2013, we saw a dramatic relaxation of spin because of the charge admixture. So now we're going to leverage that in this regime here where they don't directly mix, because now the tunnel coupling is larger than the Zeeman energy, in order to couple the cavity efficiently. Okay, so what we're doing is using the spin orbital coupling in order to make a strong spin charge dipole and get that charge dipole coupled up to the cavity. So this is the theory of it. This is with a collaboration with Guido Buchard's group with Monica Benita Gonzalez as the main author, where we look at the different orbital configurations. This is just the tunneling symmetric combination, 2 different spin states, and then I can virtually excite to the opposite orbital state, same spin state, and then with a magnetic gradient couple to this state here. So I have this sort of virtual transition through the magnetic gradient between the 2 spin states with the same orbital state. So this produces an effective coupling to the cavity based on the bare coupling to the cavity within this ratio of the detuning of this transition compared to the magnetic gradient. So it reduces the G factor by a factor of 10 or so, but you can still get reasonable amounts of coupling. And this is kind of the prediction we can make. There's a key point here. This is a 3-level system, so these line shapes are slightly asymmetric from that 3-level physics. So then Zhao Mi and Jason Pettis' group was able to build a device in silicon that does this. Here is the sort of zoom in of the actual experimental results. And here you're looking at the strong coupling regime of that cavity with a single electron spin. These asymmetric line shapes do indeed show up, and that is now consistent with this 3-level description that I just provided. And we get into the strong coupling regime by about a factor of 4. So this is a kind of a nice demonstration of strong coupling. Now we're working towards getting 2 of these qubit devices entangled with each other. How do you get around it? Well, basically, you can use this wonderful technique from Anders Sorensen's group that Florian Reiter wrote, where you use the coupling through the cavity to effectively create an enhancement of a superradiance term, which leads to entanglement of the spins under pumping. So as you know, the sort of superradiance state of a 2-spin system will rapidly decay, but the subradiant state can last for a long time. And so you can look for the metastable configuration to be the sort of steady state of driving. There's a little bit more to the story, but that's the essence of it. And so that actually leads to a pretty good infidelities of entanglement of just 1 over the cooperativity. So this system, even though it's only weakly in strong coupling, has a pretty high cooperativity because of that very long T2 of the electron spin. And so we anticipate pretty high fidelities are achievable in this system with reasonably rapid steady states. So I'm kind of out of time. I was going to talk a little bit about quantum transduction. You've probably heard about it. When we talk about these things, and there's this beautiful talk by Takeda-san on Wednesday night, and then by Koji on Thursday morning, talking a little bit about their work in electro-optomechanics. But I think these things are really interesting, where you have electrical load, you have a variable inductor capacitor circuit, a variable cavity with a joint mechanical element, because this produces a really versatile interface between microwaves and optics. You get to choose all your wavelengths. And I think that the key point here, and if there's no other takeaway message than this, if you want to start moving to arbitrary wavelengths, you really need to understand that there's a quantum regime to get into, which is the Q frequency product in excess of the temperature. That's the regime where you get multiple oscillations of the mechanical system before it dephases. It's an incredible regime to be in, to have a macroscopic system that's undergoing coherent quantum mechanical oscillation. And so, I want to return to the very beginning of what is quantum networking bias. Well, I think it can bias opportunities to start to explore what we mean by coherence in these systems. So I'm very excited about that. I'm not going to go into those details. I do want to say one last comment, as I kind of promised. So at the end of the day, what do you do with these distributed entangled states? Well, you actually start to come up with a mechanism for creating new architectures for computing. Because the architecture problem is real. Putting these things together to make a device is very challenging. There's a lot of control electronics, there's a lot of cooling needs. If you try and put 1 qubit every 100 nanometers, very rapidly you run out of space. So already back in 1999, Jan Gosman and Ike Chuang suggested that you can basically use make a deterministic circuit with non-deterministic entanglement by using what's called a teleportation-based gate. And the basic idea is you take some desired logical operation, you break it up into chunks, and then in each of these chunks you try and generate entanglement. If you get a heralding event that says you got it, then you can do a teleportation-based gate. And that ends up making a factor of 10 to 20 in overhead in your architecture, but it makes the systems problem much easier. And so we did some work on that back in 2009. I think it's really intriguing because it provides an opportunity for making an architecture where you can break out the control problem into many different subsections. So if you look at different ways of putting things together, sort of nearest neighbor coupling or deterministic resonator couplings or this distributed computing, at the end of the day, this one looks really compelling from the perspective of the control problem, of the classical control problem, of the systems engineering problem. And this is the thing that these quantum networks may enable. So with that, I want to thank my collaborators at Princeton, Jason Petta, Zhao Mi, and also here is Dave Hadjic, and then Guido Buchard and Monica Benito Gonzalez, who did some of the theory you saw. Of course, I talked briefly about the work with Koji and Takeda-san. And then these are some of the members of my group who have, some have actually directly contributed, but with respect to the work I presented today, I want to highlight in particular Michael Gollins, who spent quite a bit of time working on these things, along with Brittany and Zhang Yi, who are now working on these related topics. So thank you again for your time, and I'm happy for questions.